Okay, hi. Is my screen visible?
Yes, sir.
Okay. So let us start today's session. So this session will be on the effect of residual stress in terms of distortion happened in welding, right? So what are the causes of distortion in your weld structure? What can be the remedies to control those distortion? So we'll again understand the basic mechanisms of how distortions happen, and some equation based numericals will try to solve as discussed in the video lectures. Okay, so let us start. So the first question is very basic question. You should not bother about it is not that much complex. So better we will try to understand that what is distortion or how does this happen, right? So initially in the earlier lecture we understood how residual stress generated and what can be the effect of residual stress, and how you can control those residual stress. So starting from that, let us discuss that thing again. So because residual stress and distortion of course are directly interconnected, uh, so so basically residual stress is kind of a thermal stress, or it is induced stress, right? This is an induced stress because of some kind of thermal gradient arising from a material or some mechanical structure. Because of those temperature gradient, this kind of internal stress generated, right? So there are three principal examples of this residual stress. How does this generate? I mentioned that in my earlier lecture also. So there can be stresses induced by a volumetric change, right? So there can be either expansion or shrinkage associated with some change of phase in the material of construction. Whatever material you are considering, there can be either shrinkage depending on your coefficient of thermal expansion, or there can be expansion, right? So stresses induced by this difference in coefficient of thermal expansion, uh, basically they are linked together, right? So because of because of some mismatch in your coefficient of thermal expansion, some kind of stress can generate, and then stresses also can induce by a temperature gradient. How does this temperature gradient happen? Because of some there can be some kind of differential rate of expansion because of heating, or some change in, or rate of contraction also can vary depending on cooling within the volume of material or within the structure, right? So can you tell me some examples where this stress can generated by some phase change? Any guess? So if you think of a well-known example, can be like crushing of a wood or fiberglass hulled board by some ice formed in a lake, right? Lake or river or whatever canal. So the specific volume of water increases with change from the liquid to solid, right? So whenever you are changing your phase, changing phase from liquid to solid, what will happen whenever I'm changing the phase? A specific volume will increase, right? It will increase or not.
Yes, sir.
So if it is increasing, since the specific volume of water increases with change from liquid to solid, the increased volume of the ice squeezes on this hull of the boat. So the hull was made of some wood or fiberglass. So ice will be squeezed into that hull of boat, which will likely give before the shoreline or some bulkhead does, right? So whenever a metal solidifies after having been made molten, unlike water, its specific volume decreases. So in welding, so let us take some example on welding. So whenever your metal is solidifying after having been molten, so its specific volume will decrease, right? So this volumetric shrinkage gives rise to some thermally induced stress in the surrounding metal. So this shrinkage gives rise to thermally induced stress, right? And then what can be some other examples? So because of, let us say, let us take some example because of some mismatch in coefficient of thermal expansion. So so this mismatch of coefficient of thermal expansion giving rise to a thermally induced stress can be, maybe you have come across this bimetal strips, because of used for this sensing application. So there, the two materials which are used, they have different kind of coefficient of thermal expansion, right? So if strips of two metals with different coefficient of thermal expansion are joined along their length or whatever it is at some temperature, so as the temperature changes from the point, the material respond differently. So what will happen on heating? On heating, one will expand faster than the other while the temperature is changing, right? And more than the other when the temperature change has ceased, correct? And what will happen on cooling? The reverse will occur. So while heating, basically there will be, the rate in expansion or contraction will miss. There will be mismatch in rate of expansion or contraction, है ना? And and from thermally induced stress arising, uh, like that can be a result from a temperature gradient, as I mentioned. So yeah, can you remember any example because of some thermal gradient? Any basic physical example? So basically, let us think of like this. So when you are doing something like this, let's say you are, some hot dry glass cooking pot is suddenly placed into some cold water. So what will happen? The outside of the walls and the bottom of the glass pot cools faster than the inside, right? As a result of some thermal momentum, maybe, or because of some differentiation in this capacity of thermal dissipation, right? So some area will cool faster compared to the remaining portion. That also can induce your internal stress generation, है ना? So these are some basic idea of how your residual stress can happen because of mismatch in coefficient of thermal expansion, because of mismatch, because of some thermal gradient induced stress, those things. And uh, and this, how distortion and residual stress might arise from this same applied temperature range. So if you see, when stresses can cause, let us try to draw some figure here. Then let me explain the thing. So you have one middle portion, then here this one is having some low coefficient of thermal expansion, and then you have this, you have high coefficient of thermal expansion. Okay, so let us say this is at some temperature at T naught, and then let us think of this way. So the middle one was at high coefficient of thermal expansion, and if some temperature, if you are increasing the temperature which is greater than T naught, whichever is having the higher coefficient of thermal expansion, it will try to buckle, is it not? Because of higher expansion coefficient.
Yes, sir.
So when stresses can cause this macroscopic distortion, they will do so, right? And in the process of causing this distortion, because of distortion is happening, whatever thermally induced stresses was there during the process, it will be relieved, and it will be relieved at least to below the yield stress, and possibly to some kind of lower levels. There can be some kind of something called creep, so which is a slow process. So it may happen that it can reduce below the yield stress also, but during the process of distortion, this thermally induced stress will be relieved, right? And when stresses cannot cause this macroscopic distortion, they either cause microscopic distortion or deformation. Okay, so sorry in general, residual stress will be relieved during the process of macroscopic distortion. And if it cannot happen, if the stresses cannot cause this kind of macroscopic distortion, then what will happen? Some kind of microscopic distortion, in terms of there can be cracking or some localized yielding or some kind of localized deformation may happen to relieve themselves, or because they were locking into the structure, right? Are you getting it?
Yes, sir.
Great. So yeah, so whether a particular material or structure is able to respond to this thermally induced stress by uh, distorting macroscopically or not, what does it depend upon? This depends on its degree of constraint or restraint, how much it can restrain the distortion, right? So for convenience, the cause of residual stresses and distortion in weldments are kind of result of some these thermally induced stresses from welding, right? So those are interlinked in between. So coming to the question, which of the statement about the welding distortion are correct? Can you tell me which one will be correct?
First,
So it says that any unwanted physical shape change, it is caused by non-uniform expansion and contraction of the weld and adjustment is inevitable. I think all of the three are correct. Not all of three. It can be controlled. This is not true. This can happen now. So you can have this non-uniform expansion and contraction. So your weld metal will have some kind of expansion or contraction. Your subsidiary surface like heat affected zone will be some different kind of expansion or contraction. So these will vary depending on your location. It will not be uniform all over the surfaces of the welds, right? And of course this is true. So the third option is not correct. Agree?
Yes,
Okay. So we'll move to the next question. Says which of the material properties does not affect the distortion in the weld? So of course we know there are some kind of mechanical properties, there are some kind of thermal properties. So which material properties will not affect your distortion in weld? So there is something called yield strength, modulus of elasticity, thermal conductivity, and then your CT, coefficient of thermal expansion. So what is yield strength? We know, of course, what is yield strength. So how can it affect the distortion in your weld? So so the material which are having higher yield strength, they are having higher strength also, right? In terms of hardness, correct, no? So
yes,
whenever the material is having the higher yield strength, it is having some higher hardness also. So yield strength when it is going up, the distortion also will shoot up. So this is because after the stretching and contracting caused by this thermal cycle induced by the welding, the material is stressed to some, as I was saying, it is stressed to approximately up to some yield strength of the material. So higher the yield strength, higher will be the residual stress that will act to distort the material, right? So yield strength will affect. So okay, let me tell in that. Let me write it down. So higher the yield strength, higher will be your residual stress, your distortion also will be high. This is in terms of yield strength. Then what will happen in terms of modulus of elasticity? E. So what is modulus of elasticity? Just think it up from scratch. Like it is a measure of stiffness of a material, right? So it basically tells you what is the ability to expand or contract without plastic deformation. This is an elastic state, right? So it always tells you how much it can expand or contract without plastic deformation. So what can you expect? Higher the modulus of elasticity, it can restrain the distortion more or less.
distortion will be less.
It can restrain the material more. So distortion will be less. Welcome to the one of these questions. I'm just anyhow anyhow. Just discussing it in this question itself. No issue. And then you have something called this CT, coefficient of thermal expansion. So this is basically it's a measure of how much a material expands during heating or contracts during cooling. So higher the coefficient of thermal expansion, the more the material is going to expand or contract for a given temperature change, right? So higher CT, higher distortion susceptibility. So your CTE is high. Agreed?
Yes.
And then in terms of thermal conductivity, so it's like a measure of how easy heat can flow through a material, right? If a material is having some high thermal conductivity, let's say copper or aluminium, it can dissipate heat very quickly. So this is why we tend to get some cold starts when welding aluminium. So materials with low thermal conductivity like SS, it doesn't dissipate heat as rapidly as these two materials do, right? So in terms of distortion, a low thermal conductivity will increase the chances of it. So like SS or MS, any kind of ferrous material, they are having less heat dissipation capacity, which leads to chances of distortion more. Correct?
Yes, sir.
So let's move to the next question. It says which of the welding parameters may control the distortion during welding. So before that, before that, let us understand what can be the causes of distortion in weldments. Then it will be much easier that how can you control the distortion. So as I was saying that as I was saying that distortion can arise from this thermally induced stress, as simple as that, right? So there can be some kind of solidification, shrinkage, or thermal contraction of the weld metal during welding. So always your workpiece will have some tendency to distort, right? So what are different kinds of weld distortion? So there can be some kind of transverse shrinkage. Then you have what more? Longitudinal shrinkage. What more? There can be some angular distortion also, right? Anything else? There can be distortion in fillet welding also. So basically three fundamental dimensional changes takes place, right? One is this transverse shrinkage that occurs perpendicular to the weld line. If you try to draw the figure, so initially let us say this was your weldment. So initially this was my weldment, okay, and then let us say it distorts like this. So this is distorting in this direction. This is my transverse one, right? That is perpendicular to the weld line. Correct, no? And then you have your longitudinal shrinkage. How does it occur? It occurs parallel to your weld line. As simple as that. So your longitudinal will be in this direction. Correct? So this is my longitudinal shrinkage. And there can be, as I was saying, angular distortion, any kind of angular change that that consists of rotation that occurs around the weld line. So angular distortion may happen like this. So initially, let us say through the thickness direction, how can it look like if you are checking this side view of the weld or cross sectional view of the weld. So initially it was like this. This was my initial thing. So this is my weld bed, and then you have some angular distortion happening over here like this, right? So from here to here, this is my angular distortion due to what? Due to transverse shrinkage. Can there be any kind of angular distortion due to longitudinal shrinkage? Yes. So in longitudinal, if you see, if this was your initial weld shape, then it may bend like this. So this is something called bowing, right? So bowing is basically caused or angular distortion due to longitudinal shrinkage. Correct? Now the shrinkage and distortion that can occur during the fabrication of the weldments is actually far more complex. What I drawn here. So this amount and direction of shrinkage and this distortion, what does it depend upon? This depends basically on this mass distribution around the weld line. So kind of you can think it of as moment of inertia, the presence of other welds and their stress fields, and many more factors. There can be a lot of factors which can affect the ultimate result in your distortion, right? So if you think of this transverse shrinkage in butt welds, it's uniform along the weld line, except as altered by the through thickness effects or variation and restraint from other welds. There can be restraint from other welds also. So until and unless it is not there, the transverse shrinkage in butt weld is always uniform along the weld line, right? And the amount of transverse shrinkage, it is it is like affected by the size of the weld, like whatever is the width, whatever is the volume, those can affect your final shrinkage of the weld, right? And so the process, heat input and joint configuration, thermophysical properties, all those things matter. So if you are changing your weld metal volume, or if you are changing your heat input, these things can act as a process parameter, right? Or else if you are changing your joint configuration, and also if you are changing the material itself. So the degree of restraint applied to joint will vary depending on these things, right? So external restraint can be considered to act like a system of transverse springs, or the degree of restraint being expressed by the stiffness of the spring, right? So the amount of shrinkage can increase as the degree of restraint decrease. This is the ultimate thing, right? So degree of restraint, whenever you are decreasing it, the amount of shrinkage will increase. Agree? So since the amount of restraint almost always varies along the length of the weld, so also the transverse shrinkage can vary along the length of the weld. Normally what happened that this shrinkage, the transverse one, is greater in the center of a weld pass or run than the near the ends. So it is always greater in the middle portion compared to the end portions. And how about this longitudinal shrinkage in a butt joint? This is usually much less than what you will feel. That transverse shrinkage is very much higher than the longitudinal one. Typically some 1/1000 types of your weld length. So this can be 1/1000 of your weld length, the longitudinal shrinkage. Correct. And then you have your angular distortion, which is the result of like non-uniformity of transverse shrinkage through the thickness. And this is largely a function of joint configuration also, and the cross sectional shape. So yeah, that's it really. So which of the welding parameter, coming to the question, which of the welding parameters control this distortion during welding? So if you're having a high concentrated heat source, will it control? Or if you're having the spreaded heat source, that will control the distortion?
high concentrated research.
Right, right. So if you're having this high concentrated heat source, you can control the distortion to some extent. Then let's say you have some high welding speed. Will it control, or the lower will control it more?
Speed will control.
This is true. This is true. And if you're having high concentrated heat source, you of course will have deep penetration. So all of these above can control your distortion during welding. Right now.
Yes, sir.
So this I already discussed. Just give me the correct answer.
Second one.
Which one?
Second one.
Right. So as I was saying, high coefficient of thermal expansion will having high distortion, yield strength high also will lead to high distortion, modulus of elasticity, this will lead to less distortion. And if your thermal conductivity is high, it can dissipate heat very quickly. So distortion will, means it will not allow distortion to happen to that extent. So this is not true or not correctly matched. So correct option is two. Uh, what are the questions? ठीक है. We are here, right? In question 5. Yeah. So these also I have already discussed so many times. The development of residual stresses and distortion in fusion welded structure is due to this is very simple question actually. Both non-uniform heating and cooling. There is nothing to think of as such. So both non-uniform heating and cooling. right? No,
Yes.
can you tell me which one will be the correct one? Which of the following is not a type of welding distortion? So you have transverse shrinkage, you have buckling also, or bowing, what I told. Then you have angular distortion, and earlier in the class I talked about what is peening, right? So can you tell me what is peening? Peening is basically kind of your hammering, right? Kind of hammering
Yes, sir.
to suppress the internal stress. It's basically increasing the fraction of compressive residual stress, right?
Yes, sir.
So if you are having this tensile residual stress, what it will lead to? There will be kind of cracking, crack formation, crack propagation. It basically deteriorates your weld strength finally. So let us try to understand what can be the effect of distortion here. So we talked about what can be the causes of distortion. Let us try to figure out what can be the effect of your distortion. So if you think it in this way, like effect of distortion as the result of welding are much more obvious than the effect of residual stress. Means you can see it clearly in your weld structure after your thermal cycle, right? So what I told, this is because of the result of some unbalanced thermally induced stress in unrestrained weldments, right? So there are three fundamental dimensional changes, as I was saying. There can be transverse shrinkage perpendicular to this weld line. There can be longitudinal shrinkage parallel to this weld line, and there can be angular change, right, which consists of this rotation around the weld line. Now, the degree or extent of distortion that can be affected by several factors. What are those? Those can be your geometry of configuration. Geometry of configuration. What I mean in terms of geometry of configuration, so there can be your butt, there can be your lap, then your what else, T joint, then can be your fillet joint. So different joint configuration can have different distortion, right? Because these each affects your mass distribution or moment of inertia of your weld structure, correct? What else? That can depend upon your type of weld penetration. So in terms of weld penetration, what are those? There can be single or double V joint. There can be J type joint. Let us not go into the depth as such. Then you have your what else? Uh, then you can have your width or or volume of the weld. What else? The heat input itself. You know, the heat input. So this is heat input. What else? Anything anything more you can think of? The sequence in which the welds are made, like sequence can help your balancing or some kind of doing some offset in your thermal induced stress. So sequence of weld, and yeah, that's it really. So the obvious consequences or effect of distortion in weldments, what are those? For your weld distortion, there can be your there can be your loss of required dimension, correct? This can be effect. So especially those dimension that determine, means if it is a precision kind of thing or that determines the shape of the thing, so distortion will really affect the geometry, and then there can be some misalignment of structural elements to proper support or transfer the applied loads. Misalignment of structural elements, right? And what can be the other effects, like you can have some inability to fit one weld into the assembly of others, so inability to fitting. What else? This is a very secondary thing, loss of aesthetics. Can you think of anything more? What can be the effect of distortion? Okay, okay. This is these these are these are lot of these are lot of, I cannot actually cannot remember what can be the other effects. Anyhow, these are all. So yeah, which of the following is not a type of weld distortion? Of course, peening is not a type of weld distortion. Peening is basically is happening to suppress your internal stress generated in your structure, right? Now, what is transverse shrinkage in weld is defined as the ratio of cross sectional area of the weld thickness to cross sectional area. Which one is the true? Do you remember the equation for transverse shrinkage? Which one?
First one.
First one.
Yes.
So this was your cross sectional area of the weld. and this is your weld thickness. Hmm. This I have already mentioned. Can you tell me which one is the correct one? We are going to first today.
Second one.
So it says your angular distortion occurs in a butt weld when transverse shrinkage is not. Yes. Good. So are these questions common of what in this semester you are getting?
The assignments.
Yes or no? Some of them. Some of them.
Yes, some of them are.
Okay. So angular distortion occur when transverse shrinkage is not uniform in thickness direction. Okay, let us do some quick math. Says if you're having some 10 thick plate that is joined in butt configuration by this SMAW using some 500 amperage of current, what will be the longitudinal shrinkage? If you remember the equation, it's just a equation based question. Put the value and give me the answer.
First one.
Which one?
First.
So what was the equation? What was the equation for longitudinal shrinkage?
3 IL
It's equal to 3 into I into L is your length of the weld, and then
L into 5.
thickness into 10 to the power 5, right?
Yes. Yes.
So you are having some 500 amp of current, and then uh, L is not provided, and then you have your 10 thick plate, and then 10 to the power 5. So it's finally coming into 15 into 10 square by 10 to the power 6. So it's 15 by 10 to the power 4L, that is equal to 0.0015, 0.0015 L, right? Move to the next question. So this is for fillet weld. You need to estimate the longitudinal shrinkage. Take your time, and if it is not happening, then we'll discuss. Anyhow, we'll discuss after you provide the answer. So for this fillet thing, I have directly provided you the area. So if it was like this, if you had this length L1 and you have this length L2, then also you can get the area half into L1 into L2. Here I have provided directly what is the area of the fillet portion. So one part is the area of this structure, and another part is the area of the fillet.
1.84.
It's done.
Yes.
Okay, okay, okay. So what is a basically for fillet is coming. A fillet is okay 50 into 2, that is for two fillets, which is 100 mm square. And what is AP is coming as, this is
1
my
kg.
8 into 100, that plus 8 into 70, right? So this is 800 plus 560, this much of square, that is equal to 1360 square. Then what you have done, you are checking the AP by AW or A fillet, right? What it is coming as, this is something 13.6, which is
13.
less than 20. So so the empirical formula you can use here, like the longitudinal shrinkage will be 25 of A fillet by AP, right? So this is 25 into 100 by 1360, this much of So what is the final value?
1.84.
9.8.
1.84.
1.84. Okay, so it was 1.84 I should have a better handwriting. 1.84 Great, great. We have moved too much quick today. Good. So this is also again one of those quants where you need to put the value in your equation and just uh, get the value out from there. So distortion in multiple restrained fillet welds. What is the equation? Do you remember?
First one.
First one. So if this is the first one, so for you, this multiple restrained fillets like this, and here this is restrained, right? Like this. So this is your span length. So Yeah, if the first one is true, can you find out the angular distortion for these values are provided already, where L is 1000, X is 50, and your change in angle will be 9 degree. That must be converted to radian.
It's coming 109.9.
109 point. Okay, 109. Let's say around 109. Okay, so what is phi coming as? Phi in radian?
0.157.
So let me take it as 0.16 radian. So your delta by L will be really 0.16 by 4, that minus 50 by 1000, which is 1 by 20, minus half, that into 0.16, right? Correct, no? So you are having this 0.04. Am I doing right? 0.04 minus 0.05 minus. Am I doing anything wrong? No, no, it's fine. This into 0.16, right? How much is this coming? Means this part. Ultimately, this will be plus. Point zero 0.05. Just let me check. 0.05 minus 0.5. This minus 0.45, that into 0.45, that into 0.16, 0.072 plus 0.04. How much coming for you? 0.112, that into L, 1000, 112, around that.
Yes, around that.
Right, no? Okay.
Yes, yes.
So I also got the right value. Great. This is the last question, really. So, what is welding sequence for large surface consisting of several plates? So, before that, there is uh, another thing. There is another thing to discuss. Like, how can you control? How can you control or remove this distortion? Like, so to prevent some kind of distortion, what is happening? There are several viable approaches, right? So, the first thing is distortion can be minimized by proper design. That is the base. So you must design it properly so that uh, you can come up with some less distortion in your weld structure. What does it mean? It means that, among other things, one, you should employ the minimum number of parts and thus some minimum amount of welding. That is the ideal, right? If you are doing some minimum amount of welding, or you are using some minimum number of parts, your distortion will must reduce. That is the ideal case, but the reality check will be different depending on your application, of course. Now, second, what can be done? You can prepare your joint properly, right? Especially for unrestrained butt joints. If you are preparing it properly, you can minimize the angular distortion. Like, you can use some double V or W, or some means, basically you can do the double thing to oppose the single V or single U configuration, to balance that heat input or shrinkage, whatever is there. You know what else? Thirdly, you can do some, like, you can use some minimum sized fillet wells. The fillet, whatever you are using, that can be of minimum size, right? So, and also the distortion can be minimized by proper assembly procedures also, such as you can do some presetting the members to compensate for angular distortion, or you can do some assembling the weldment so that it is nominally correct before welding, and then use some form of restraint to minimize the distortion from welding. And and finally, of course, there is sequencing of welding to balance this heat input and create some, as I was saying, you can create some offset in your shrinkage or distortion. So, what is the advantage of this presetting thing? The advantage is that there are few or no residual stresses once the part has been welded, or yeah, there will be no residual stresses as such. So, and a consequence of, if you are doing some rigid fixturing also, there can be a consequence. Is the consequence is that it introduce some kind of residual stress at the expense of this freedom from distortion, right? So proper sequencing certainly helps to minimize this distortion, but also results in residual stresses also. So there must be some balance in between this residual stress and effect of residual stress, that is your distortion. You know? So yeah, as I was saying, proper sequencing, that always helps to minimize this distortion, and but also that results in your residual stress, as the structure is eventually forced to fit together somehow, and You can always do some preheating also. Preheating can be used to reduce this distortion in a weldment by minimizing this temperature gradient, है ना? So yeah, so uh, how can you do a presetting? Let me draw some figure that will be beneficial always. So you can do something called presetting. You can do something called presetting. So then you can do this rigid fixturing. Then you can do like sequencing of welds. And yeah, that those are the three things I just mentioned. And lastly, I mentioned that preheating can be used. Preheating can be done to reduce this distortion. So once this distortion takes place, you should remove that distortion, right? Or you should remediate that distortion what is happening there, right? So there are two options. What are those? So one is your thermal straightening, using the heat to cause this compensate this expansion or contraction. So this is basically called something called flame straightening. Okay, and then you can have mechanical straightening. One is thermal and another is mechanical straightening. So in mechanical straightening, what can we do? We can use some presses or some kind of jacks. So mechanical straightening is always easier to understand. That is why it can be very much common unless structures are very much large. So flame straightening is understandable in principle, that like in practice this is more artistic. है ना? So but it offers tremendous capability actually, even for very large and apparently immovable structures, correct? And mechanical straightening is very straightforward. So as I was saying, you can use some braces or jacks to straighten the part itself. If some kind of distortion is happening, uh, yeah, yeah, that's it really. So coming to the question, what is the welding sequence for a large surface consisting of several plates to control the welding distortion? Should I do the transverse one first and then the longitudinal one, or it should be vice versa? So as I was saying, the transverse one will be the highest compared to the longitudinal distortion. So of course, if you are doing the transverse seam first and then do the longitudinal one, you'll get some balance in your distortion and you will end up with some less distortion. Are you agreed? Or it should be vice versa? Which one will be the right one?
First one.
Yeah, that's what I was saying. The transverse seam should be welded first, followed by a longitudinal seam. This is true. That's it, really. If you have any question, so today we moved so fast actually because the distortion is linked up with residual stress in some amount. That's okay. But we spent some time to understand what is happening, what is not is happening. How can you remove those distortion? What should be the welding sequence? And then uh, how these distortions generate in terms of its effect? What can be the causes? If you have no question, we'll end it up here.
Yes, sir.
Okay. Okay. Let us end it here. We'll meet. We'll meet next week again. Bye bye.